I guess this. Okay, wait. Let me see. Okay, we are now live. I believe so. Let's see. Yep, we are already live. So yes, welcome to my another live stream. Yeah, live work. So yeah, today what? So today what we're gonna be doing is reaction rates, equilibrium, and half-life problems. This one here comes from my. No, sorry. This thing comes from the OCW of MIT. This is this is from the class of 3.091 practice problem J. So yes, all of these questions comes from practice problem J of 3.091 MIT OCW. So without further ado, let's just actually get started. Let me just first just do that first. Sorry, let me just turn off the Bluetooth first. Okay, so here we go. Okay, iodide reduces Fe3 according to the following reaction. 2 Fe3 plus, yeah, this is this guy here. This guy here is Fe3 plus 2 iodide in a aquifer would react into 2 Fe2 and 2 iodide. No, iodine, sorry. This one here is iodine. So, experimentally, it was found that doubling the concentration of Fe3 doubled the reaction rate, and doubling the iodide concentration increased the reaction rate by a factor of 4. What is the reaction order with respect to each species? What is the overall rate law? What is the overall reaction rate? Okay, so yes, let's actually just get started by doing this first. Um, the speed or the rate in this case would equal to k of o k of fe3 plus. Let me just do that. Fe3 plus. Can I just beat this guy to a superscript? Yes, I believe I can. Yeah. Well, except for the plus. Let me just do that manually. Fe3 plus no. Okay, so let me just do this manually. Fe3 plus to the power of to the power of m. That's what we normally do. Okay, so that means that yeah, superscripts only work with numbers. So let me just do that manually again. So k times Fe3 plus m, multiply that by the concentration. Let me just change that again. By the I minus or iodine. So let me just go ahead and just add another superscript there. And then we are back into our normal script to the power of n to the power of n. There we go. So that is basically the formula to so that is the formula to actually find what is the reaction rate would be. And yes, this k here is a constant. So yeah, let's just go ahead and just try to do something with this. just by doubling the concentration of Fe3. Okay, okay. So we can actually just assume this, okay? We can just assume something here. Let's say that the concentration, oops, let me just turn that thing back. Nope, 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 nope. Just turn this guy back into normal script. There we go. Fe3 plus the concentration of it. Yep, there we go. The concentration of Fe3 plus, we can first assume that yes, for the first reaction it would be A, and then when you double it, you could just write it as 2 times A. Oh, let me just go ahead and just put this guy back. What? 2. Huh. Normal 2 of A. There we go. And then for the third one it would be A, because we are just doubling the iodide concentration, just to make this a bit much more simpler. So that would be our first experiment data. The second one would be the I minus, so let me just copy this all. Oh, let me just, oh wait, from there, oh, there we go, yep. Let's copy that, paste that on the other side there. The concentration of iodine, firstly it was B, and then it resulted to, and then for the second experiment it would be another B, because we didn't actually change the iodine, and then lastly it would be 2B for the last data, because we just doubled the iodide concentration. Oh yeah, it's iodide, not iodine. So yeah, that would be that. And then the rate would be, firstly the rate was C. That was where we started. If you have like, so if you have a concentration of A, no sorry, A concentration of iron 3 is A, and then and then and then you add it by the concentration of B. No, sorry, the concentration of iodide, which is B. The rate would be C molars per second. But then if you actually just see this again, for the second experiment, it was the like the reaction rate actually doubles, so that would be 2 times C. But then for the third one, when you double the iodide concentration, the reaction rate increased by a factor of 4. So that means it's 4 times C. And so with this data, you can actually determine what is M and what is N. So let's actually go ahead and just figure that out. So there are multiple ways for you to actually find M and N. The first way is just by doing a bit of ratio work. So yeah, let me just copy this guy first, and we will just do the ratio work first. So first, let's just write every single equation that we got. So we got the rate C would equal to K, a constant, multiply that by the concentration of Fe3 plus, which in this case it was A, multiply that by iodide, sorry, the the concentration of iodide, which in this case it was B, and that's our first data. The second data that we got was this 2A, no sorry, 2C, that is the rate of the second data that we got, equals to K, a constant, multiply that by the concentration of Fe3 plus, in this case it was 2A. Don't forget to put a bracket around it, and then you multiply that by the concentration of iodine, which in this case it's B to the power of N. Good. And so finally, for C, sorry, let me just paste that first. There we go. The rate, in this case it's for C, equal to K, a constant, multiply that by the concentration of iron 3, that would be A, multiply that by the concentration of iodide, that would be B, no sorry, that would be 2B. And so with this 3, you can actually try to find each of their reaction order. So let me just do this first. So that was the first bit. So that was the first data, second equation, sorry, and then the third equation. So with all this, we can go ahead and just determine what the reaction rate it is. Firstly, you can just actually say that yes, equation 2 divided by equation 1. What would that be? So yeah, reaction 2, that would be 2C divided by C, would equal to this guy divided by, let me just move that guy down again. There we go. Move that guy down. Divided by this guy. And so with this, you can actually see what you need to do. You have basically found what 2C divided by C is. That is 2. Let me just turn that back. Oh. How do you turn this thing back normally? That, nope. Well, let me just turn off my superscript. There we go. So yeah, that's 2. Multiply that. So yeah, 2C divided by C, that's 2. That would equal to, the K here can be crossed. This guy and this guy can be crossed, so that would be 1. And then 2A to the power of M divided by A to the power of M. So let me just go ahead and just write that down. 2A to the power of M to the power of M. Let me just write this down. No, let's just copy it instead. Divide that by 8, divided by A to the power of M. Wow. Let me just go and do that. There we go. And so with this, you can use some power law to actually find what what M is, because yeah, you know the power law and how it works. So yeah, basically for the power law, in this case it would be just M here would be distributed among each of them. So that would be 2 to the power of M, multiply that by A to the power of M. But then a to the power of m divided that by a to the power of m would be 1. So yeah, the answer would be 2 to the power of m. Let me just copy that instead. Enter that. No subscript, please. There we go. So 2 would equal to 2 to the power of m. So this would conclude that m would equal to 1. Okay, so that would be the first one. Sorry, let me just do that again. M would equal to 1. Okay, so now all we need to do is to try to find what n is. So yeah, the simplest way is to actually just to try to find 3 divided that by 1. Same thing as before, but yeah, instead you'll actually get 4 equals to 2 to the power of n. I won't do a lot of the maths, so let me just go ahead and just do that quickly. To the power of n there. So what you'll get is actually n equals to 2. And so yeah, that's basically the solution for our first question. What is the reaction order with each species? So let's actually just go ahead and just write that down. The reaction rate for Fe3 plus, that's 1. For iodide, that's 2. Okay, so now let's actually go ahead and just try to find the overall rate law. So the overall rate law is basically this guy here. Copy that, paste that. Yep, there we go. Paste that guy in. And so when we put this guy in, this should be a power of... Oh, sorry. There shouldn't be any power for Fe3. And for n, that will be to the power of 2. And that's basically the overall rate law. I believe so. Let's check for the overall rate law. The rate law is rate versus temperature. I guess, yeah. Or like, yes, there is also like a different way for you to actually to write it down, but yeah. Oh, but yeah, this one here should also work. So yeah, that's basically for our second question. And lastly, what is the overall reaction order? It's basically 1 plus 2, which would equal to 3. And that's all answered actually covered. But there is actually a much more simpler way for you to actually to solve this problem. The first thing is just by actually realizing something. Watch. Let me actually just change this guy here. Yep, there we go. So yeah, let me just click that first. Make it a bit much more smaller. Yep, there we go. Okay. So from here to here, it only changes by 2. Same thing here to here. The A only changes by 2. That means that 2 to the power of so basically it states 2 to the power of something must be equal to 2. In this case, it must be 1. But what about this one here? This guy going to here, that's 2 to the power of something must result into 4. In this case, that would be 2. And you have basically solved your your reaction order with respect to each species. And then you can just straight away write this guy and then just find this guy. Pretty easy. And that is how I will gonna be doing that a little, like yes, a little bit much more later on. So let's actually go and just do the second question. Benzoyl peroxide is a medication used to treat acne. Its rate of thermal decomposition at several concentrations was determined experimentally, and the data were tabulated as follows. Experiment 1, 2, 3, and 4, benzoyl peroxide of 0, that is basically the initial, in molars that would be 1.00, 0.70, 0.50, 0.25. And then this is the initial rate, that's 2.22 times 10 to the power of negative 4, 1.6 times 10 to the negative 4, 1.2 times 10 to the negative 4, that should be negative 4, and then 0.59 times 10 to the negative 4. What is the reaction order with respect to benzoyl peroxide? What is the rate law for this reaction? So before that, let me just fix my nose first. So I'll be right back. Okay, I'm back. So yeah, basically the way for you to actually to look at this is that yeah, I recommend you actually getting yourself a calculator because yeah, this thing helps you a lot. And yeah, basically you know what this guy divided by this guy is. It's simply 0.7 and then etc. This method would be very easy for you to actually do that with. So yeah, let's let's go ahead and just go ahead and open our scientific calculator. So yeah, let's first actually check what's 1.64 times 10 to the negative 4 divided by 2.22. So 1.64 divided by 2.22. That's around, this guy here is around 0. No, no, let me just actually just write that guy in straight away. This guy here is 0.74. Pretty accurate, I should say. And then 1.12 divided by 2.22. 1.12 divided by, oh, that's pretty good. 0.50. It's very close. And then lastly, 0.25. 0.25. No, sorry, 0.59 divided that by 2.22. That would be 0.27. Pretty accurate, I should say. So yeah, basically that there's like no other powers in here because like yeah, it is already pretty accurate. And yes, reaction orders are basically integers. So yeah, you just need to try to find the most accurate integer. In this case, it would be 1 because like yeah, this guy to the power of that guy must result to that guy. So yeah, the solution in here would be 1. And what is the rate law for this reaction? And yeah, the rate law is gonna be very simple for you to write, and that is, let's go ahead and just do that. Rate would equal to the concentration of benzoyl peroxide. Don't forget to multiply the front side by K. And that's basically it. See? Reaction rates are basically pretty simple. So yeah, we are still actually talking about reaction rates. So yeah. I don't think we have anything about, yeah. we don't have any we don't have anything about equilibrium, so yeah, I will later just change the I will just change the title. So yeah, that one. Half-lives for the reaction A plus B to A plus B C were calculated three values A naught, three values of A naught, and the so yeah the initial rate for A would be 0, yeah, sure, and B was the same in all cases. The data are listed in the following table. Does this reaction follow first order kinetics? On what do you base your answer? Okay, so basically we are talking a little bit of half-life. So half-life is basically um, the time it takes this time here. So yeah, it would be the time to make that A here, A during that time, divide that by A naught. That's basically it. And so yeah, with this here, I just need to figure out how do you do this. Um, let's see here. Half-life. I have actually written a little bit of Half-life. Ln 2 over k, 1 over k of A naught. Yeah, that's the time. Okay, okay. So, yeah. I might not know a lot about this Half-Life stuff, but I can at least predict. So, okay. So yeah. So yeah. So yeah, the rate reaction for a zeroth order, that would be, oh wait, wow. Okay, okay. Divide that by 2k, but k is constant. If it is first order, it should be ln 2 over k. But that actually means that there's no such thing as... Oh wow. This would be a little bit of a hard thing to find. The ln 2 of k equals to... Okay. First order ln 2 equals to 2, that's 3. Okay, okay, okay. So, basically, first order kinematics is basically the first order. So yeah. So yeah, basically, that for the first order, the half-life is basically ln 2, the natural log of 2, should equal to 1 over k. So what this states is basically that this guy must be a constant. This guy here should be a constant. Should be a constant at any time. So the answer would be it is not constant. And yeah. And yeah, the answer is basically it is a first order reaction, I believe. Oh no, sorry. No, sorry. I think it's a third order. No, sorry. It's a second order because 1 over k, that's a constant. Multiply that by a naught, but the a naught is actually at the bottom. So yeah. So, you know what? I don't know. How do I actually do this? Well, yeah. I know. I struggle. But yeah. Basically, we know that first order is basically always a constant for its half-life. So yeah, we can just be saying that, yeah, no, and yeah, we can And yeah, we can prove it from this guy here. And that's actually how you actually try to find this. I think that's the correct answer. So yeah, let me just go ahead and just fix my nose again. Okay, so with this now, let's actually go and just solve for number 4. So, number 4. An enzyme catalyzed reaction has an activation energy of 15 kilocalories per mole. How would the value of the rate constant differ between 20 degrees Celsius and 30 degrees Celsius? If the enzyme reduced the EA, the activation energy, from 25 kilocalories per mole to 50 kilocalories per mole, by what factor has the enzyme increased the reaction rate at each temperature? Okay. So, I don't know how do you actually solve this, but yeah, according to my instincts, this guy here should, yeah, that guy there should actually tell us a little bit about what we need to do. Activation energy, yep, there you go, activation energy, which means that it should be Arrhenius, and yes, and here we also have temperature. That means that, yeah, it's basically Arrhenius. And so Arrhenius is basically, let's try to find it. Where did I write my Arrhenius? Okay, so rate is basically equal to a constant, multiply that by E to the power of negative of the activation energy, divide the thing by the KB. No, wait, should I use KB instead of the other guy? Uh, let's see actually. Like, yeah, I forgot a little bit of the unit, so yeah. Joules per mole, yeah, so yeah. So yeah, instead of using um, KB, the Boltzmann constant, instead we will use RT, the the ideal gas constant, because in here we are using moles. So yeah, that's why we are using the the ideal gas law constant. So yeah, with this here, it has an activation energy of 50 kilocalories per mole. Okay, so that means I need to try to find the value of the R. Okay, okay. So yeah, basically it's asking how would the value of the rate constant differ between 20 degrees and 30 degrees? It would differ because of this guy here. So yeah, let me just actually go ahead and just think about that. So yeah, before that, let's actually just write this guy. Rate equals to A, multiply that A, multiply that by E to the power. Let's go put the power sign in. There we go. Minus E of A. Subscript that. I hope I can. Nope, I cannot. Well, so yeah, I guess that should work. EA divided that by RT. Okay, so the first thing that we need is that, yeah, from our information that, yeah, we have already found what EA is. The, like, yeah, the, like, yeah, the activation energy. Let me just go ahead and enter this. The activation energy would be 15 kilocalories. Yep, let me just go that equals to 15 kilocalories per mole. And then the R here, the Boltzmann constant, it's 8.314 joules per mole Kelvin. The first temperature, T1. T1 here is the T1 is 20 degrees Celsius, which is 293 kelvins. 293. Let me just actually change this guy a bit. I don't, I don't really like it. So let me just change that up there. T1, yep, there we go. I guess that's a bit too small, but oh well. And then we go to normal numbers. Okay, yep. That will be 209. Oh, why does this thing happen now? There we go. 293 kelvins. T2 is 303 kelvins. Like, yeah, basically to convert Celsius to Kelvin, it's just by adding 273. So yeah, let me just actually add a subscript there. There we go. That's better. There we go. So, okay, wow. My nose is starting to do something. So yeah. So from here we are trying to find how would it differ. Um, I think the best way for you to actually find how much it differs is just by dividing one by the other. So yeah, let's actually just do that. Let's go ahead and just try to find the difference. So yeah, the ratio. And yeah, basically on this theory it states that yeah, if the temperature is lower, it would mean it would have a it would have so wait, sorry. So if the temperature is lower, the power would get very low. And so E would be very near zero. So the rate would be something low as well. Okay, so let's just actually go ahead and just find what rate 2 divided that by rate 1 would be. When we do that, we can actually just cross out the A because it's a constant. And then after that, we can just try to find what e to the power of negative A of RT here. But before that, I'm still intrigued by this one here. Because this is still at joules per mole Kelvin. But the thing that I want is actually calories or at least kilocalories. So the way to do that is to just try to convert it, but let's see. Joules to calories. Okay. So let's just put it into our calculator here. 8.314 314 would be 0.00199. Yeah, let's just write it like that. 0.001987. Yeah, sure. Kilocalories per mole Kelvin. So yeah, basically, how did how did I do this? I don't know. Why? Because I don't even remember how to convert calories into joules. But yeah, I don't really use calories to joules or joules to calories. But yeah, this time I need to. So yeah, with this guy here, let's actually just divide the rate 2 by the rate 1. That should be e to the power of negative a, blah blah blah. That should be. Let me actually just write this guy down. E to the power of negative ea. The negative ea here is negative 15. The units are still the same. Divide the thing by the r. That's 0.001987. And then we would just basically multiply this by the difference. So yeah, it's 1 over 2 1 over 293. No, sorry, 1 over 303. Subtract that by 1 over 293. How did I get this? Well, basically, I use, so yeah, that's basically the exponential rule. So yeah, the ratio would be, let's see, wait, first. Okay, yeah, so yeah, I'll let you just actually just edit that out because yeah, pretty noisy. So let's actually go ahead and just put this guy inside of our calculator. It's some crazy number here. So yeah, e to the power of negative 15 divided by 0.001987. Yep, it's undefined. Oh wait, no, sorry, I forgot that like yeah, that should be negative. Divide that by 1 over 303 minus 1 over 293. 293. That's so the ratio is 0.427. So yeah, basically the ratio of rate 2 over rate 1 is 0.427, which means that I think I did something wrong. Wait, if the temperature gets higher, the number should get closer to 0. Wait, really? If, no, sorry, if the number gets higher, the thing should get nearer to 0, but okay, yeah. Basically, I don't know my maths. I'm, like, yeah, but like, yeah, my mind is basically crazy right now, but yes, I think it's correct, but also wrong at the same time. I don't know how. Let's just actually recheck it because because it doesn't really make sense. What I'm doing is rate 2 divided by rate 1. So rate 2 divide that by rate 1, that would be 1 over 303 minus 1 over 293. And wow, there might be something wrong. Huh. According to my mind, there's something wrong. But I cannot actually determine what is it. The rate must be something, right? Like what I find is actually the ratio. And if rate 2 divided that by rate 1 is a number between 1, that means that rate 2 is something lower. But yeah, the math doesn't make sense now. What I'm hoping is that the negative should actually cancel each other out. Oh wow. Oh wow. 1 over 303 minus 1 over 293. You know what? I will later just recheck this guy and yes, probably make a video separated. But yes, it might need a little bit more thinking. So yeah, next up here, number 5. Is my audio on? Yeah. So let me just put this guy here. Is that better? Yeah, I hope so. So yeah, the data in the following table are the rate constants as a function of temperature for the dimerization of 1,3-butadiene. What is the activation energy for this reaction? So for this, why K is what 1 over m big y? Wait, I don't. Wait, what? Let's see. What's the activation energy? I don't think it's that, no. Let's see here from my notes. The rate K, oh, there's an there, and some bugs. Okay, what is the activation energy? Um, that's molars. Oh, wow, this is a bit much more complicated. Um, but as the temperature increases, the other thing increases as well. But this guy changes, that means that should be the rate. Yeah, I believe that's the rate. So yeah, instead let's actually just assume that that's the rate. So let's say, for example, that yeah, we know some fact that yes, the rate here, which is K, must be equal to A, multiply that by E to the power of something, yeah. But there is a different variation for this, and that's actually the natural log of the rate subtracted by the natural log. Now you know what? No, let's don't don't use the natural log because it might get complicated. But yeah, rate 2 divide that by rate 1. We are using the same theory as before, which something that I was not hoping to do, but oh well. Must be E of the negative EA over RT. Should it be R? Um, let's just use R because yeah, we want to try to find this in per moles RT at that of T2. Add that by EA over RT of 1. RT1. So, how should we do this though? I'm like, okay. I think let's just actually go and do this guy with this guy. It shouldn't really affect a lot. So yeah, let's just plug it in straight into my calculator. So 645 divided by 600. Yeah, that's 1.07075. Yeah, and then you take the natural log. Oh wait, do I need to take the natural log? No. Well, yeah, I've taken the natural log, and then we need to try to find what EA is. But then this guy here, this top side here can't be converted into EA over R of 1 over T1 minus 1 over T2. So let's just try to do that. That should, so yeah, EA over R, so, so basically, the answer that I just got needs to be divided by this 1 over T1 minus 1, yeah, that guy. That's 1 over 645. No, sorry, 1 over 600 subtracted by 1 over 645. That's 621 now. Well, that's in kelvins, so yeah. And then after that, I just need to multiply this by the R, which in this case I'll use 8.314. That would be, so I would get that EA here would be 5171 joules per mole. That's what I just got from all my calculations. So yeah, I think that's the correct answer. But yes, I will later need to double check it. So yeah. So yeah. If it is wrong, yeah, I will make a new video out of it. So yeah, next up, let me just clean my nose a little bit more, because yeah, I don't know why, but yeah, my nose is a bit blocked. So yeah. Let's try this, okay? Number 6. At higher altitudes, ozone is converted to O2 by the reaction of O plus O3 in the ozone would result to 2O2 with a rate constant at 220 Kelvin of 6.8 times 10 to the negative 16 centimeter cube times moles. Wait, rate constant. Wait, but that's 1 over molars second. Like yeah, centimeter cube, it's basically milliliters. Okay, what's the overall reaction order? Huh. Huh. Like yeah, this thing actually makes me a bit much more curious, because like I know, but yeah, but yeah, molarity is basically moles per volume. But then this one here is actually flipped, so it's 1 over ms. Oh wait, but that's the rate constant. Is this top side here also a rate constant? But the rate constant shouldn't change, right? Oh, okay. So I think, so yeah, basically this guy here at the top there should be something else. Oh, where was the one that I was actually confused with? But yeah, for this guy here, I still don't understand. But yeah, for this guy here, I mean, I made a mistake. How did I see this? Oh wait, oh wait, oh wait. Let's see. I still don't understand Arrhenius. So yeah, Arrhenius should be like some sort of those other thing. Let me just let me just search Arrhenius. Um, let me just quit this guy first. Arrhenius law. Yeah, Arrhenius equation. The K, which is the rate. Oh, okay. So, oh wow. So that's basically the rate constant. Oh wow. Damn. That could have changed something. But luckily it doesn't. So yeah, this thing here is not rate. Instead, it's K. It's K. So what that means is that it is just a constant. So yeah. So 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 it doesn't mean rate. Instead instead it actually means constant. So what I just actually calculated was the constant. Um, was the ratio between constants. But that thing would mean one thing as well. That this guy here, what I calculated was wrong. In fact, this guy here is is not a constant. So yeah. Oh wait, sorry. But how would the value of the rate constant differ? And this is what I just already calculated. So in fact, I have. So in fact, I just figured this out as well. Wow. So yes, according to my theory that yeah, the constant that so yeah, the one that I just found is the constant actually differing. So yeah, I still don't understand. So yeah, let me just write this guy down first. Okay, there. Okay. So yeah, the only thing that would actually differ would only be the A, but yeah. Let me actually just also check this guy as well. K equals to A times negative A over T and then negative A over. So yeah, sorry. So yeah, instead here should be a K. K is the rate constant. So what I just found is actually K2 divided by K1. But then according to my theory, let's just assume that K1 would be the guy. So with a with a lower temperature, let's say 293, yeah, something happens. Oh, oh wow. That should be 1 over EA over RT. So then we just need to check like how far does it actually travel. Like yeah, for example that if the power is actually no sorry if the T is lower, that would mean that RT that EA over RT should be high. But then if you have a higher T, that means it has a lower EA over RT. Yeah, yeah. So yeah, basically when the T is lower, the EA over T is higher, but not the negative A. So yeah. That would literally mean that constant 2, no sorry, constant 1, wait, what? Yeah, const so yeah, this thing here is already true. I know, like, I know the difference between the constant now. So that means that, yeah, my answer is already correct. And so, now let's actually just try to find the other one. If the enzyme reduced the EA from 25 kilocalories to 50 kilocalories per mole, by what factor has the enzyme increased the reaction rate at each temperature? Okay. So, this guy was asking that, yeah. What? So yeah, I should actually just do this straight away because what I just found was, oh wait, what just happened? What I just found was actually that, yeah, I like, yeah, I only found the difference, no sorry, the ratio, but yeah, let's just calculate each of them, shall we? So let's go ahead and put the subscript in. There we go. 1 K1 would equal to, so just put all those things. So that would be 8 times. Let's just use my calculator here. E to the power of negative 15. Yeah, negative 15 kilocalories per mole. Divide that by 0.001987. The bottom side is also multiplied by the temperature, 293. 293. So that would give you 6.464 times 10 to the power of negative 12. 10 to the power of negative 12. Okay, so that's the first constant. Let's copy that, paste that. Okay, so let's just go back to regular size. But this is still just go up and down. Where is it? No. Okay, so yeah. Let's actually go ahead and just try to find this. So yeah, let me just go back to normal size. Right, K there. Yep, there we go. K2 is equal to 8 times. This guy, the only difference is just the temperature, which in this case it's 10 to the power negative 11 of 1.51288. So let's just go to there. Yeah, pretty accurate. So that's basically the thing. So yeah, how would it differ? It would differ by some factor. Let's just go and just try to find what K2 minus K1 is. So yeah. Let's just actually ignore that first. And so if the enzyme reduced, so yeah, how would the value differ? So yeah, how would it differ is basically trying to find ratio or the difference. But yeah, I think for this type it would be like the factor, I believe. So yeah, let me just copy here some of these here. Copy that, paste, copy that, paste. This would be a normal negative sign. There we go. This would equal to, so yeah, this guy here, K2 minus E to the power of negative 15 divided by 0.001987. Multiply that by 293. So the difference is actually, let me just go ahead and just print this guy. Yep, there we go. Would equal to A times 8.664. Yeah, pretty accurate. But you need to multiply that by 10 to the power of negative 12. So yeah, that's basically the difference. And so what happens when the enzyme actually reduces the EA to 15 kilocalories? So when it actually reduces, oh wait, no, sorry. Oh, okay. So what happens when the EA is actually, let me just go ahead and just try to find the thing again. Okay, so the EA, yeah, sorry, let me just, I should just copy this instead. So the EA would be 25 kilocalories per mole. The question is, what would the, so what would be K1 and K2 would be? It should be pretty similar, I should say. So yeah, let me just copy that first. So same calculation, but yeah, instead we will be using the 25. So let me just go ahead and just remove those guys first. Subtract them by 25, so yeah. We got ourselves for K1, no sorry, for K2, it's negative 19. That's the constant, multiply that by 9.254. And for K1, that would be multiplying that by 2.83, that would be 2.243 times 10 to the power of negative 19. So we just need to try to find a factor. So by what factor has the enzyme increased the reaction rate at each temperature? So by what factor? That means that, yeah, the ratio. So basically what I'm going to be doing is actually doing this. We'll start by e to the power of negative 15 over 0.001987 multiply that by 293, but then you add it again because that's at the bottom, so yeah, that would be like 10 times, so yeah. Okay, so yeah, basically what I just did is that, yeah, what I just did was actually just changing some stuff, so yeah. But yeah, the difference, so yeah, what I just did was I actually rearranged it. But yeah, it's still, but yes, for the general formula, it would be like K1 divided by by the old K1. So yeah, let me actually just write this guy here. Ratio for K1, that would equal to 28,817,506. Like yeah, that's, oh wait, 0.5. And then for the ratio for K2, that would be, let's actually just change the temperature. That's 16,347.43.17. So yeah, it changes by a lot. Like yeah, you just multiply this by a crazy number. So yeah, it's a very good. So yeah, we have already found this. And yes, if you have any question, just go ahead and just leave it on the chat. because yeah, I'm scared that someone actually doesn't understand how did I just get all of these numbers. So yeah. Next up, at higher altitudes, ozone is converted to O2 by the reaction of oh yeah, that guy. So yeah, what I have finally discovered was that the K was actually, oh wait, no, actually for this one here, okay. So basically the K here is 6.8 times 10 to the negative this guy here. Let me just copy that. The K is this guy. But then you need to realize something about this. The units in here is basically 1 per molars second, 1 per ms. It's 1 over ms. This basically means that, so this would mean that the overall reaction order must be 2. How do you know that it's 2? The fact is that for the K of the overall reaction of a second order, it would always be 1 over ms. For like yes, for first order it would be m over s. For first order that would be 1 over s, and for second order that would be 1 over ms. And if I should just finish this, oh yeah, I did. Good. So we have discovered that it's 2. So B, what is EA for this reaction if A is 8 times 10 to the power of negative 12? Yeah, that. So with this is basically Arrhenius again because we got the EA there. So let me just copy this guy here. Whoops. Let's put it on the other side here. So yeah, for part B, the formula is this guy. So we can just rearrange them all. So that's basically K. K, that would be 6.8. 6.8 times 10 to the power of, oh wow, 10 to the power of negative 16. Yeah, that. But yeah, the units, we don't really need to care about the units because like yeah, we can actually just cross those units anyways. Divide the thing by the EA, which is, no sorry, by the A, which is 8 times 10 to the power of negative 12. And then you take the natural log of the answer, that's negative 9.3, and then you just need to multiply that by a negative 1 because it's negative EA over RT, and then you just need to multiply the thing by the R, which, should I use joules? Yeah, I'll just use joules. So yeah, the answer, we want to multiply that by 8.314. That's the R. So yeah, R units is joule per Kelvin, and then we just need to multiply that again by the temperature, which is 220. And so what we get is that EA would equal to according to all my calculations, that's 70,143.71 joules per mole. Well, yeah, that is some crazy number. But yeah, that's 4 joules per mole anyways. Because like yeah, I'm not I am not doing this with with atoms. So yeah. And so if chlorine is present, the rate constant at 220 Kelvin becomes 3.7 times 10 to the negative 11 centimeter cubed times mole Q to the power of negative 1 times seconds to the power of negative 1, with A equals to 4.7 times 10 to the negative 11 centimeter cubed times molecules per over negative 1 times seconds to the power of negative 1. Calculate EA for the depletion of ozone in the presence of chlorine. So we just need to modify a little bit of the equation. We just need to use the K and the A of the following things. So yeah, luckily I am using Desmos, which means that I can just change a little bit of the numbers, but yes, at the bottom it should be the same. So yeah, I really recommend for you to use Desmos. That's 3.7 times 10 to the power 4.7 times 10 to the power negative 11. And I believe that's the number. Wow. Wait, really? Oh yeah. So basically, the answer that I got, the same thing in joules per mole. That would be 437.57 joules per mole. And so now, show an energy level diagram for these two processes, clearly labeling reactants, products, and activation energies. So basically for this, we just need to sketch a bit of the graph. This is the energy, this is like the plot for reaction. So yeah, this is reaction. So basically, the depletion of ozone would basically, let's just assume it starts from here and then it just ends right over here, and it ends right at the bottom there. But yes, unfortunately I don't really know anything about these types. So yeah, let's just assume something like this. So the way that it works is that you need to go very high up and then going back down. This guy here is basically the activation energy for without Cl, chlorine. But then you can also just catch a new one right there. This one here is the EA, activation energy with Cl. So there we go. So just by so you just actually found your energy level diagram there. And if you were an environmental scientist using these data to explain the effects of Cl on ozone concentration, what would be your concentration? Well, here's the thing. Ozone protects us from UV. That means that, yeah, we don't want our ozone layer to be depleted. That means that I would say Cl is, so yeah, Lucy-Else is dangerous. Dangerous. So yeah, that's basically my conclusion. And so, let's go to number 7 here. Let me just go there. There we go. Let's go up. Okay. So let me just go ahead and just clear my nose again because yeah, I don't know why. But yeah, my nose is blocked. Okay, here we go. The decomposition of hydrogen peroxide, H2O2, can be represented by the following reaction. H2O2 would result to H2O plus O2. The table below reports data taken at room temperature, 300 Kelvin. Show that the reaction is first order. Second, calculate the value of the half-life of this reaction. Suppose that the initial condition of H2O2 was 3.5 molars. How long would it take at 300 Kelvin to reduce the concentration of H2O2 to 25% of its initial value? Okay, so for this one, let's actually just go ahead and just do this, shall we? Show that the reaction is first order. Okay. Um, let's see. I don't want to assume this guy, but this guy. That's basically one of the worst ways for you to actually solve this. So I need to try to find one that would be effective. I guess these two can be used. So yeah. So yeah, basically you need you need to remember about one thing, that this guy here is time. And so what time is basically 1 over the rate. That is what is normally used. T equals 1 over the rate. So yeah, you just need to make sure that that is on your mind. And so let's just actually go ahead and just try to find the ratio between those two. 0.62 divided by 0.25, that's 2.48. 2.48. And then for the backside there, that would be 3000 divided by 1800. That's 1.6. Following. So, I cannot conclude that the reaction is first order yet. Huh. Unfortunately, I can't. What about this guy and this guy? This guy might be able to solve this. Yeah. Yeah, I don't think so. Sure that the reaction is first order, but but unfortunately, I don't think it's first order. Oh wait. Oh. Okay. Okay. Sure. 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 So so yes, this thing here is a little bit of a trick question, I believe. Wait, I don't think it's a trick question because the answer is the rate. What about if I actually just try to find what the thing is? So yeah, just try to find the log of the thing. Would that be correct? Uh, this should be 2.4, 2.45 to the power of n must do result to 1.6. Uh, let's try to find what n is. So n is basically the log of 1.416 is divided by the log of 2.48. That's 0.5. It is pretty weird, but I think you can actually use another method, which is just by making a graph out of it. Like yeah, sometimes graph could help you determine what what the reaction is. So yeah, let me just start with a blank graph, just make a table, and yes, I'm making this graph at my phone, so yeah, I'm so sorry if you guys didn't actually see it. But yeah, let's just start 0 with 2.32. Add with the 2 at second 200, it's 2.0. At 400, that's 1.72. At 600, the thing is 1.49. At 1200, okay. At 1200, that's 0.98. At 1800, the thing is 0.62. And then at 0. And then at 3000, the thing is at 0.25. Okay. Okay, so let's actually just zoom this guy out. What I got is a little bit of a curve, which might indicate that it's a first order. Oh wait, I think I know the way. So yeah, let's just make a new table stating this guy to be x1 as well. This guy is y2, but then we need to say that y2 equals to x. No, y2 equal. No, sorry. Like yeah, y2 must equal to. What is the integrated law? Okay, yeah. I found the integrated law. For the first order, it would be you need to plot it with the ln. Okay, so let's just go ahead and just say it's the ln of y1. Yep, x2 that. So that yeah, x1. So no, sorry. So x2 equals to x1. Wait, what? 1 times x1? Is that right? No. No. This code header can be defined elsewhere in the calculator. Um, can I can I just state that to x1? No. Well, oh yeah. Let me just go ahead and just plug the entire numbers in there. 400, 600, 1200, 1800, and 3000. Wow, that's a straight line. So yeah. Okay. So basically, I've I have actually found how to actually to solve this. So yeah. So basically, if you actually join the lecture, which was lecture I don't know how many, but yeah, it was about rate reaction. If you actually just join that lecture at OCW, you you know some facts about how do you actually graph these guys as a form of those as 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 a form of like some sort of time. So yeah. So like yeah, this guy here is time. This guy here is, let's say this guy is our H2O2. What 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 I just got is something like this. It is it is not a straight line, but if you plot it like this with this guy still H2O2, but the difference is actually, but the difference is just, it's just by putting this guy into lunch, the natural log, and this is time. What you'll get is actually this, a straight line. And yeah, you can just plot this on your graphing calculator, but then, so yeah, this is, but then you could also just plot this as 1 over H2O2, and this would try to help you to determine if it is a first order, second order, or zeroth order, first order, or second order. So yeah, let me just go to that, plot that against time. So let's just go ahead and write this, that y3 will be equal to 1 over 1, 1. So let's go ahead and just make a new table. This would be y3, this would be x1, x2, x3. 0, 200, 400, 600, 1200, oh whoops, 1200 is there, this is 1800, yeah, and then lastly it was 3000. So what I got, if you actually just plot it against 1 over t, it would be something like this. It's not a straight line, so yeah, it is out of the way. So yeah, from this fact, we have found that it's a first order. First order. So that's why we love graphs. And so now the question is, calculate the value of the half-life of this reaction. Well, for a first order, a half-life is basically this. The ln of, well yes, obviously you can also just determine it just by doing this, but yeah, I don't know how to do that, so yeah. So yeah, let's actually say, okay, so for the half-life, it's actually ln 2 over k. I believe so, right? Let's check. The half-life for a first order reaction, it's ln 2 over k. Yes, ln 2 divided by k. But then we also have this fact, okay? We have the fact that the slope here is actually negative k. So we can determine what the value is. So yes, we just need to find what k is. So first, let's actually just go ahead and just look from my graph here. Let's go and just assume this point and this point. Yeah. Okay. So the slope here. So the slope is y over x. So yes, the y, the change of y here is actually negative. Is 0.884. So yeah, that's y2 minus y1. That's 0.6981. Subtract that by 0.8416. Divide the entire thing by um, the temperature 200 there. So yeah, let's just go ahead and just calculate that. 0.8416 subtracted by 0.6981, divide that by 200. The k here, we found I found the k, 0.00007175. Wow, we have managed to calculate this. So yeah, that so that is the k, and so with that we can actually just do this now. take the natural log of 2, divide the thing by 0.00077175. And so we know what the half-life is. So the t here, the time that it would take would be 966.06 seconds. Oh wow. We have finally managed to find the time. So yeah, I'm pretty happy about this, but then yeah, suppose that the initial condition of H2O2 were 3.5 molars. How long would it take at 300 Kelvin to reduce the concentration of H2O2 to 25% of its initial value? Okay, so this thing here requires a little bit of context. So yeah, let me just try to find this. Okay, so because this is a first order thing, so the rate would actually equal to negative d of a divided by the dt, which is equal to the constant of a. So yes, from this information we have found. Wait, no, sorry. The rate of the thing. No. It should be the negative 1 over 2. Yeah. It's negative 1 over 2 times that. Yep, there we go. Why is there a 1 over 2 there? It is because of the coefficient at the front there. We need to be careful about the coefficient as well. So yeah, that's why I include the negative half there. But actually, I don't really need to care about the half because it would later actually go involved into the k, and that k would be like constant, which I've already found. So yeah. So yeah, let's actually just integrate both sides. Yeah, because we are now just solving a differential equation now. So basically a here. So yeah, the concentration of A would be Ka over dt. Integrate that, which is the one that I'm not going to be talking about how you actually find that thing because it's going to be hard for you to find it. So that's why I'm just going to leave that later on. So yeah. So you just integrate both sides by dt. That means that you integrate that side by dA. So that would be A. So dt must go there. Wait, what? Oh yeah, sorry. I forgot the A must go to the other side first. So yeah. Negative d. So yeah, when you actually just integrate that thing, it would be ln of A must equal to. So that side goes to the other side there. And then after that, you just need to integrate what kt is. That would be equal to t, no kt. And then you add it by the initial condition. But then I forgot that the thing is negative, so yeah. You need to add that, and then you just need to add that by the ln of A naught. So wow. That took me some time. But yeah, it works, I guess. So yeah. This is basically the integrated one. That means that we know the so that means this guy. So yeah, this time we know what is the concentration of A, which in this case should be H2O2. And so all we need to do is to try to find. Okay, so what we are trying to find is this guy here to be this guy divided by 4. Yeah. So if we do such things, I will actually just move K2 to the other side, must be equal to ln A minus A, so that would be ln A naught divided by A, that would be the ln of 4. And so, K must be equal to ln 4 over K. So, I can just put that thing, ln 4 there, that's 1932.117576. And seconds, yeah. So, I have finished this. So yeah, I know some of these. I just actually just solved it right now, and yeah, it's pretty crazy. But yeah, theoretically, that yeah, you just need to sum this guy again. Yeah, you just do a double sum. But yeah, I just solved practice problem J here. And how long did I take? Around 1 hour and 40 minutes. So yeah, if you have any questions, you can just go ahead and just leave it at the comments, because yeah, I don't think I explained a lot about how to actually integrate the thing, but yeah, my best recommendation is for you to actually watch the lecture. But yes, I believe that this practice problem could be solved as long as you know of as long as you join the rate reaction lecture at OCW. So yeah, thank you very much for actually watching the stream, and